Hello. You are here on the channel about XRD analysis. The presentation is made by Manfred Wiesner. So, the channel is about X-ray diffraction analysis techniques. In this video I would like to answer the question: what can I read out from the diffractograms? What do the diffractograms say about my examined material? To answer this question, I would like to create a short video now. Typically, the material under investigation by XRD is crystalline. Today I would like to bring an example. It concerns measurements which were carried out in a high-temperature chamber HTK 1200 from Anton Par. The investigated material was a powder metallurgically produced high-speed steel. Typically, milling cutters are made from it. It is important that the material is properly heat-treated. Only then it develops the correct property profile in the applications. The diffractogram shown here was recorded using chromium K-alpha rays. In the diffractogram you can see peaks coming from 4 different crystalline structures. The 4 phases show peaks, some of which overlap strongly. The blue curve is the measurement. The red curve shows the calculated simulated diffractogram. The Rietveld method was used for the simulation and will be discussed in a later video. The question is: what can I read from the diffractogram now? The quantities of the individual structures. That means, the quantities of the individual phases can be determined from the peak area or from the ratios of the peak areas. Deviations from the ideal peak ratios in a single phase indicate texture. Texture occurs when the individual X-ray domains are no longer randomly distributed. From the peak positions, the Bragg equation can be used to determine the lattice planes of the corresponding peaks. The cell metrics, that is, lattice parameters and the angles of the unit cell, can be determined from the lattice planes. Among other things, the lattice parameters are indirectly influenced by the chemical composition. Different atoms and ions require different amounts of space in the unit cell. In steels, the interstitially dissolved carbon and/or nitrogen amount in the cubic face-centered austenite. A higher dissolved carbon increases the lattice parameter. The body-centered phase martensite or bainite is distorted tetragonally by the carbon. In particular, the A-axis increases proportionally with increasing interstitial dissolved carbon. The C-axis remains approximately unaffected. A little more exotic are the effects of stacking faults, which cause peak shifts, depending on the lattice plane. Stacking faults lead to a positive or negative shift of the lattice plane. Perhaps we will make a separate video on this topic one day. So, as a last point, I would like to consider the information that can be obtained from the peak width. A frequently non-negligible part of the peak width comes from the measuring device. Often the measurement is done with copper K-alpha rays. Since the emission consists of 2 components, there are peak duplets. The emission lines have a natural line width, which is also responsible for a certain amount of peak broadening. From a nearly defect-free sample, the influence of the instrument and the emission profile can be determined at the peak positions. Often this is determined with lanthanum hexaboride. The actual peak broadening caused by the sample depends on the lattice defect density. The defect density can be determined for each individual phase. The point defects contribute to the local change of the lattice spacing. More significant are one-dimensional lattice defects such as dislocations. The local influence on the lattice plane spacing is also one-dimensional. Normally, with sufficient dislocation density, the influence of point defects on peak broadening can be neglected. We would like to come now to the summary. From the diffraction peaks 3 important information can be derived. First, from the peak areas the phase quantity as well as the texture can be estimated. Second, from the peak position the lattice plane spacing can be determined. Among other things, The spacing is indirectly dependent on the chemistry. Third, the peak width is a measure for the lattice defect density. Especially the dislocation density has a strong influence. In this context, the influence of the measuring device often cannot be neglected. Thank you for your attention.